Good morning, everybody. Any question from last class? Can you just check whether you are being recorded or not? I forgot. Then I have to exit the entire screen and come.
Yes,
Is the
Yes, sir.
recording on? Is the recording on?
yes, sir. Yes, sir. It is recorded.
Okay, very good. Any question from last class? Okay. Anybody? Okay. You have no question, fine. So in the last class, we ended with simple cubic unit sum. We talked about the number of nearest neighbors, which called coordination number 6. But however, I said I'll try to demonstrate certain things by crystal model. So today I brought the model for symmetry elements. So I shall switch on my video. Please let me know whether you can see it or not. Can you see myself with a model here? Hello?
Yes,
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Okay. So if I have a cube with me, and if I put an imaginary plane like this coaster through it, then this is called the image plane. Right side of the cube is the mirror image of the left side of the cube. So this plane passing through this crystal, just like this figure here. This is the mirror plane. So A1 becomes the mirror image of A2. So this is A1, this is A2. This is the mirror plane. So this is mirror symmetry. Now we'll talk about the rotational symmetry. I said opposite face centers. This is the face centered position. This is a face centered position. Two opposite faces, an axis is passing through. I have a cube. You see, at the center of each face, there are 6 faces. There is a drilled hole. I am passing a steel wire through this. Can you see me well?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So you look at, there is a sticker here in front of my cube, just to show you where I start with. So you see a cube, and I'm passing an axis through the center of 2 opposite faces. Now I rotate the cube by 90 degrees. What do you see?
It
Do
is
you
not.
see a cube?
Yeah.
I rotate it by another 90 degrees. What do you see? Do you see a cube?
Yes, sir.
Now I rotate by 45 degrees. Do you see a cube or something different?
Something
Different.
If I rotate by another 45, means total 90 degrees, you see the cube?
Yes, sir. Yes.
Now I rotate by another 90 degrees. You see the cube?
Yes.
Now my sticker is back. So how many times I rotated to get the sticker back?
4 times. 4 times.
4
times.
60 by 90 degree makes 4. So this axis joining the center of opposite phases is called four-fold rotational axis. Four-fold rotational axis. Now I join the body diagonal, 2 composite edges. You see, let me do it this way, it will be easier for me because sticker is facing towards you. Along the body diagonal, I pass my square rod. You see a cube?
Yes, sir.
Yes, sir.
I rotate by 120 degree. Watch it, how I rotate it. What do you see?
Q.
Cube. Another 120 degree. What do you see?
Cube.
Now another 120 degree.
Cube.
Cube.
Cube and the sticker is back. So 360 by 120 is 3. So this axis is threefold rotational axis. This is the one along the body diagonal. See, if I rotate by 120 degree 3 times, I get the sticker back. 120, another 120, third 120. You got the sticker back. So it's a threefold rotational axis. This is the symbol, a triangle. Two-fold rotational symmetry is a square. Now to opposite edge centers. One is here, the other is here, that axis. Now, two opposite edge center I join by this axis. This is the sticker there. Watch carefully. I rotate it, rotate it, rotate it, rotate it. Then, after 180 degree rotation, I get the cube. Now another 180 degree rotation. Do you see the cube?
Yes, sir. Yes, sir.
With the sticker back. So basically 360 by 180 makes 2. It is two-fold rotational axis. Two-fold rotational axis. Look at it. One fold, you got the cube back. Second fold, you got the cube back. With the sticker on. This is a two-fold rotational axis. Now if you look at it, A1 here, the number 3 here. With respect to the body center, my wire, this point is the mirror image of this point. So this is called inversion center, the center of that cube. Now, this one I mentioned roto-inversion. You rotate it along a four-fold axis. A1, it comes here, and then invert it about this body diagonal position. You got this point A2. So A2, this one is the roto-inversion of this one. Okay, just 1 second, please. Any question do you have? Anybody?
No, sir.
This figure at the left, this is the closest packing of spheres I mentioned yesterday. You cannot get higher density of occupation of space by spheres than this arrangement in any other arrangement. And if you look at that figure, I have table tennis balls, and this is how I arrange. This is the close packed plane of atoms. You cannot pack these table tennis balls or spheres closer than this. Now, if you look at this simple cubic lattice, I said there are 8 corners. Each corner is occupied by an atom, but 1/8 of that atom is inside this particular cubic unit cell as shown here. So if you look at towards my palm, I have a wooden ball sitting at the corner of this unit cell. Any corner, let's assume this corner. You're looking at it. Okay. So this, can you see this? So this sphere is occupying one corner. So how much is inside? 1/8. I can divide this sphere or this wooden ball into 8 parts. 1/8 of it, 1/8 of it is inside this cubic unit cell. So 8 corners multiply by 1/8 makes 1, and there will be number of atoms per unit cell equal to 1/8, equal to 1. 8 corners multiplied by 1/8. Now, today we shall move to this atomic packing factor I calculated. The next crystal structure we shall talk about is body-centered cubic. If you look at this model, holding in my hand, there is an atom at the body center position and 8 atoms at 8 corners of this cubic unit cell. 8 atoms at the 8 corners of the unit cell. Within this particular unit cell, I have 1/8 of that atom, 1/8 of that atom. 1/8 atom at each corner, which is lying inside this unit cell, and one completely inside the unit cell sitting on the center position. So for the sake of brevity clearance, the corner atoms are shown here by red color ball, and the body center position balls are shown as white ball here. So this is the schematic. What I am holding in my hand is equivalent to this diagram. So how many atoms per unit cell? 1/8 at each corner. 1/8, 1/8, and so on, 8 corners, and completely 1 atoms inside this unit cell. So 1/8 into 8 plus 1 center atom makes number of atoms equal to 2 in body centered cubic unit cell. So what is the coordination number? You can consider this center atom, number of nearest atom, 1, 2, 3, 4, 5, 6, 7, and 1 behind that, 8. So 1, 2, 3, 4, 5, 6, 7, 8. With respect to this center atom. But if I consider any of this corner atom, any one of those, how many nearest neighbors are there? The answer is
6.
8. 8. You do the calculation in front of you, take the notebook, draw the things, you will come with the answer 8. So, and along the body diagonal direction, along this body diagonal direction, the atoms are touching each other. The atoms are touching each other along this body diagonal position. This is the field model, how the atom ionic radii are touching each other. This is a ball and stick model, but this is how the unit cell is filled with atom. Some common metals, chromium, tungsten, alpha iron, allotropic form of iron, tantalum, molybdenum, etc. are body-centered cubic. They have 2 atoms per unit cell and their coordination number is 8. So if I consider any of these, if we consider center atom, easily you can see along the body diagonal they are touching each other. So have 8 nearest neighbor. So coordination number 8. If you consider any of those corner atoms, you will get the same answer. 8. You do it in front of you now. The same thing I showed you. Number of unit cells more than one here. There's a 1 unit cell here. And then like this, you have several unit cells here and so on. And this is body-centered cubic. Any question? How do I calculate the atomic packing factor? Simple calculation. Lattice constants are A because it's a cube. In which direction atoms are touching each other? At the body diagonal direction. If their radius is capital R, R, another R, another R, another R, 4R. And the body diagonal length with respect to this edge A will be root over 3A. Root over 3A is the length of the body diagonal of this cube whose edge length is A. And along the body diagonal, there are 3 atoms are touching each other. So this length in terms of the radius will be R plus R plus R plus R, 4R. So 4R is equal to root 3A. Number of atoms per unit cell, 8 corners, 1/8 atoms. So 1/8 into 8 makes 1 plus 1 in the body center position, total 2 atoms. So atomic packing factor will be the volume of the atom, 4/3 pi R cube. What is R? Root 3A by 4, that whole cube. And number of atoms, 2. Total volume of the unit cell, A cube. So that makes 68, 0.68, 68%. For body centered simple cubic, it was 52, 0.52 or 52%. In case of BCC, 0.68 or 68%. So atomic part, who is more densely packed, simple cubic or body centered cubic? Definitely body centered cubic. Instead of 52, now it is 68%. Now we talk about face-centered cubic structure. Any question? Are you there?
Yes, sir. Yes, sir.
Yes, sir.
Now tell me, how many atoms are there per unit cell without looking at these writings?
4.
4.
Is written 4 atoms per unit cell. It was 6 phase into half. Why half?
Because they're shared by 2 lattices, unit cells.
Why not 4?
It's on it lies on the face center, so the face would be common to 2 lattice, the 2 unit cells.
You look at a model here, face-centered cubic. So this is a face-centered atom. I have another unit cell of face-centered cubic. I put them together. So these face-centered atoms, this face-centered atom is half of this face-centered atom. They make one together as such. So each face is occupied by face-center position 1 atom shared by 2 side-by-side unit cells. So each face-centered atoms have half of it inside one unit cell. So 6 faces into half, that makes 3. There are 8 corner atoms. 1/8 into 8 equals to 1. So 3 plus 1 makes 4. So there is no body center position. So number of atoms per unit cell of face centered cubic is 4. Metals like aluminium, copper, gold, lead, nickel, platinum, silver have a structure face-centered cubic. Because of these, face-centered cubic has unique properties which will be told slowly, that it has a much higher ductility than any other crystal structure with respect to metals. Face-centered cubic metals are more ductile than body-centered cubic, simple cubic, hexagonal, close-packed, and so on. Its coordination number of nearest neighbor is 12. You can consider one of those corner atoms. Oh, by the way, atoms are touching each other along the phase diagonal. Along the phase diagonal, the atoms are touching each other. Okay, they are touching each other along the phase diagonal, like this. Oh, sorry. Oops. This is a phase diagonal position. So difficult to draw it with this. So they are touching each other along the phase diagonals. You can choose either any one of those corner atoms or any one of the face-centered atoms and find out each atom is touching 12 nearest neighbors. This is your homework, and you will find out the coordination number 12. So this is a homework. What I'm telling it that you prepare it, and I will tell you to submit to the TS, and you have to submit it. Along the phase diagonal, choose a face-centered atom, show coordination number 12. Choose any one of the corner atom and show the coordination number 12. Means show the number of nearest neighbor is 12. This is your job with nice schematics. Explain it. This is how show there are several face-centered cubic unit cells side by side. So now we want to determine the atomic packing factor for face-centered cubic. Just now I mentioned the atoms are touching each other along the phase diagonal. So phase diagonal length, you choose this one, 1 r, another r, another r, another r, 4 r. This one equals to, what is this phase diagonal length? If each edge is a, root 2a. So how many atoms are there per unit cell? 4. The volume of in a cube, how much volume is occupied by 4 atoms? 4 atoms multiplied by 4/3 pi r cube. What is r? R equals to root 2a by 4 cube. What is the volume of the unit cell? A cube, and it comes to 74% or 0.74. Simple cubic. What was the atomic packing factor?
0.52.
0.52.
152.
Face-centered cubic?
168.
What is
0.74.
face-centered cubic? Hey, there's a mistake. This will be
Yes, sir.
okay. This will be face-centered cubic structure. Is 74. So which is the most densely packed unit cell so far what you have studied? Face-centered
It's a
cubic.
Center.
Now we move to hexagonal close packed structure, or it is also known as close packed hexagonal, CPH. HCP, hexagonal close packed, or close packed hexagonal, CPH. They are synonymous. You see in the book so far in your high school books, you saw a unit cell just like that, and it was called close packed hexagonal. Actually, it is not. It is only 3 unit cell consist of. 1 unit cell is this. Okay, so there are 8 corners. Each corner has 1 atom, and there is inside of each unit cell there is an atom which is at 1/3, 2/3, half equivalent position in coordinate system. If we calculate, the coordination number of it is 12, just like close packed hexagonal. Do it in your as a homework. You also calculate its atomic packing factor 0.74, assuming the C by A ratio. C is the vertical axis, A is the 2 other basal axis. Ideal packing, it will be 1.633. Show me for ideal packing, C by A ratio should be 1.633. It is a simple geometry. Do that. And considering that geometry, you will find the atomic packing factor 74%. Coordination number 12, you determined and do that. And number of atoms per unit cell is 2. Now, how they are arranged? Here, if you look at this picture, I'll show you. Watch carefully. The bottommost layer, these dark color atoms, these dark color atoms, these are lying on the bottom, these dark color green atoms, just like this. Can you see my model here? I'm holding this close packed table tennis balls.
Yes, sir.
Now the next layer of atoms is the blue color one. Where do they sit? The dark color circle, this is the closest packing of the spheres. You create 1, 2, 3, 4, 5, 6 unoccupied space like this. Look at my finger. These are the unoccupied space between the spheres. 1, 2, 3, 4, 5, and 6. Can you see it clearly?
Yes, sir.
Yes, sir.
Now, the second layer of atoms, they are close packed also. Here I showed 7, but instead I showed 3 here. Same thing, same packing. What I did, I put them in the alternate holes. Means, if you look at it, every alternate hole, 1 here, 1 here, 1 here. Above that, I put the blue color atoms. Look at it, just like this. Can you see it clearly? Each blue color atoms, my right hand side, this set of balls, sitting on the valley. Valley means this every other hole here, leaving one in between. Now the third layer of atoms, this light green color, like this, It sits exactly above the bottom dark green atoms, just like that, just like that. Means just above it, this atom sits. Just above it, this atom sits. Just above it, this atom sits. And what does the blue sit? In this every alternate hole. This is how I pack the highest atomic density plane, the close packed planes. These are close packed planes in this fashion. And this sequence is called A, B, A, B stacking. A atoms are dark green ones. B atoms sits at the alternate valley positions between the A atoms, dark green one. And what does the light green one sits? Just above their corresponding dark green atom, just like that. So what I did, this one matches with this. So what I get, looking at it, you can see it. Does it look like a close packed hexagonal structure? Hexagonal close packed synonymous?
Yes.
Yes, sir.
These packing of atoms are called A, B, A, B, A, B packing, one after another, this stacking sequence. Stacking sequence of what? Close packed planes of atoms of the highest atomic density, they are touching each other. So if I stack them like A layer, B layer, next layer will be just above the A layer, next layer will be just above the B layer, next layer will be just above the A layer. In this sequence, if I put A, B, A, B, A, B stacking sequence of this close packed layer of atoms, this is called hexagonal close packed or close packed hexagonal unit cell. Metals like cadmium, magnesium, titanium, zinc, they have a close packed structure. Coordination number 12, last like FCC. For ideal C by A ratio, that you have to calculate all these things for me, homework 1.633. For that C by A ratio, the atomic packing factor 0.74. Same as face-centered cubic. But here I am raising a question which I will answer next week. Face-centered cubic has atomic packing factor of 0.74. Coordination number 12. They also have close packing of atoms. I'll show you just like this. But face-centered cubic unit cells or metals have lot more ductility than the metals having close packed hexagonal structure. Why? That question we shall answer. Any question?
Sir, can you please repeat the last part?
Which one?
Sir, ductility.
Huh? Exactly which one? You please tell me.
Sir, the question which you mentioned right now.
What question?
Uh, the ductility of comparison between.
I say my question is, both face-centered cubic and hexagonal close packed have coordination number 12 and atomic packing factor 74%. They also have this close packing of atoms, the one I showed you. But face-centered cubic is a lot more ductile compared to hexagonal close packed. This is my statement. Read up the textbook and I shall answer this question perhaps next week, if not today. Most likely next week. That is my statement. Do you follow it? Hello?
Yes, sir.
Oh. Any other question? So this is a unit cell of closed packed hexagonal or HCP, 8 corners, and there is an atom inside it, the unit cell. Its position is 2/3, 1/3, half, or 1/3, 2/3, half, whichever you say it, inside it. This is the coordinate of the inside atoms. So that hexagonal things you see, actually that consist of 3 such unit cells. Now you can calculate the theoretical density of the material, mass of atoms in unit cell by the total volume of unit cell. This is the formula, where n is the number of atoms per unit cell, A is the atomic weight, V suffix C is the volume of the unit cell, which is AQ for cubic system, and Na is the Avogadro's number. By putting these values, you can calculate the theoretical density. So for example, if we take the case of chromium, which is body-centered cubic, number of atoms per unit cell 2, atomic number, atomic weight 52, if we assume gram per mole, R is 0.125 nanometer or 1.25 angstrom. Number of atoms per unit cell small l is 2. And along the body diagonal, they touch each other. So in terms of A, that is constant, with respect to these, we can calculate 0.2887 nanometer. So theoretical density from this number of atoms, 52 is the atomic weight, volume of the unit cell A to the power 3, and this is Avogadro. This is your number, Avogadro's number. I get theoretical density as 7.18 gram per centimeter cube. Actual density, if we can measure it experimentally, it's 7.19. So that's pretty good calculation with these values. The metals generally have higher densities than ceramics, and ceramics have a lot higher density than polymers. So if we plot the density values here, for metals, from magnesium, lightweight metals, to heavy gold, tantalum, platinum, it goes like this. Then ceramics, it's like there, graphite is low density material, zirconia is higher density in ceramics. These are for polymers and these are for composite materials. So we plot it this way. The question is, why metals have higher density? Because they have close packing of atoms, metallic bond, and are often large atomic masses. Ceramics have less dense packing of atoms in the unit cell and often lighter elements. Polymers have low packing density. Quite often they are amorphous and they consist of lighter elements like carbon, hydrogen, oxygen. And composite, depending upon the constituent materials, its density values have it falls under intermediate range. Any question? Hello?
No, sir.
Now what I showed you a short while ago, a model, A, B stacking, and you get a 3 unit cells of close packed hexagonal. You can see the model well?
Yes, sir.
Okay. Now I'll do another demonstration. This is the basal plane of HCP. Can you tell me, is there a difference between this arrangement and that arrangement of balls or spheres? Is there any difference in their arrangement? You see, they are identical. Here I showed one extra atom and I removed these two outside. This is the closest packing of spheres. I cannot get any closer packing between the spheres than these two. Same thing. Just assume top two are gone and bottom I added, because this can be added in infinite space. That is the definition of a point lattice. So this arrangement and this arrangement are identical. So now what I do is this. This is a close packed planes of atoms. Let's call this hole B, B, and B, and the central one as C. So this is a B hole every alternate B, and this central one is C. The next layer of atoms. In close packed hexagonal, what stacking I did?
AB.
So now another close packed planes of atoms, I put it, these three atoms just above the B hole. Okay, can you see this? So central hole is the position C. In hexagon, the next layer of close packed planes will be sitting just above the A. But instead, what I did, I put only one atom I'm showing, but this is the part of the entire close packed layer of atoms. I put it at the C position, which was previously unoccupied in the case of HCP. So what stacking of atoms I have right now?
ABC.
ABC.
Now, the A layer is towards me. I have a layer of atoms. So behind A, what should be the layer of atoms? Which position?
B.
No. A, B, C. Behind A, what should be the layer?
C.
C. So
C.
exactly on the C position, I am putting this atom. So what sequence I have now? C, A, B, C, right?
Yes, sir.
Yes.
Now
Yes,
look
sir.
at it carefully. How does it look like?
Sir, FCC.
What is the stacking sequence now?
ABC.
ABC.
What was the stacking sequence of hexagonal close pack?
AB.
AB.
Now let me repeat this experiment. This is the A layer of atoms, close packing. This is a B position, this is a B position, this is a B position. This one is C position. So next layer of atoms, I put it just above the B position. This is C position, unoccupied. Put the next layer of atoms at the C. Behind A, there will be a C layer of atoms I put in the C position. So the stacking sequence is C, A, B, C. Above, in front of C, I can put A layer, B layer, C layer, again A layer, B layer, C layer, and so on. But here I put C, A, B, C. I turn it around. What happens?
FCC.
Now if I do this, A layer, B layer, above A again, what is this? What is this?
HCP.
HCP. So if the close packed planes of atoms are stacked in the sequence of AB, 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 They are called close packed hexagonal or hexagonal close packed. If the stacking sequence is A, B, C, A, B, C, A, B, C, then it will be called face-centered cubic. So the stacking sequence of atoms, which are on close packed planes of atoms, will determine the crystal structure. They will differentiate between a body-centered cubic, a close-packed hexagonal, and face-centered cubic. Any question? Any question?
No, sir.
Now, this figure, this is common. AB sequence, close-packed hexagonal or hexagonal close-packed. Now the planes I showed you stacked in ABC sequence are these triangular shaped planes in face-centered cubic unit cell. So they are stacked in ABC, this sequence. What are the crystallographic index of these planes will be taught later on. But you see, the stacking sequence of the close packed planes determines the mechanical properties, as well as other properties, principally the mechanical properties of HCP metal in contrast to face-centered cubic metal. Same atomic sequence in this basal plane as well as this triangular shaped plane. But the stacking sequence is different in face-centered cubic, where it is ABC, 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 whereas in HCP, AB, so on. So you can read Shackelford's book as well as Callister or Reed Hill for this crystallography section. Now I'll take a 5 minutes break and then I will start the next part of the class. Any question? Okay, I'll take the break. Hello everybody. Now we are going to look at certain crystal structures, common ones, and see how they look like. Remember, I mentioned the definition of a point lattice and 14 Bravais lattices or 14 Bravais point lattices. And I said the atoms are located on those points or about those points. A group of atoms about that point. Now that is very important. This is a structure of cesium chloride structure. Tell me what is the Bravais lattice for this?
So body centered cubic.
Okay. The open circles are cesium atom. These are cerium atoms and these are chlorine atoms. Fine. So if I stand here, and look at this body diagonal direction, I said any point of the point lattice I can stand and look at any direction and get a view. So I stand here, look at the body diagonal position. What do I see from here? What do I see?
Cesium.
A cesium.
Cesium.
Now I move here and look at the same body diagonal direction. What do I see? What do I see?
Chlorine ion.
A chlorine ion. So what is the definition of point lattice? I can stand at any point of the point lattice, look at a particular direction, whatever view I get. I move to any other point in a point lattice and look at the same direction, I must get the same view. So standing here, looking at the body diagonal direction, I see a cesium ion. Randomly, I can choose any point. I can choose a point here, but here, anything. What do I see? A chlorine ion, not a cesium ion. Do I get the same view?
No, sir.
No.
No, sir.
So what happens in this structure? I take a pair of ions. Pair of ions. This pair, one pair of atom. One chlorine ion, one cesium ion, a pair, and assign that pair with respect to this corner position. So chlorine is sitting on the corner, cesium away, half the body diagonal away from this corner position. But as a pair, this pair is assigned to this point. Similarly, there will be a pair of cesium ion and a chlorine ion. And this pair will be assigned to this corner point. Similarly, for each corner position of a point lattice, you have a cesium ion and a chlorine ion. So a pair of ions, cesium and chlorine, is assigned with respect to these corner positions. So the crystal structure will be, a Bravais lattice will be, anybody?
Simple cubic.
Simple cubic. So Bravais lattice is simple cubic, and the materials having this kind of structure are called, of course, simple cubic, but more specifically they are called cesium chloride type structure. Cesium chloride type structure. So number of ions per unit cell will, instead of 1, it will be 2. 1 cesium ion, 1 chlorine ion, because this pair is assigned with respect to each corner. So 1/8, like simple cubic you did. So there will be 2 number of ions, 1 cesium ion, 1 chlorine ion. It is, of course, Bravais lattice is simple cubic, but materials having this kind of structure is called cesium chloride type structure, and the Bravais lattice is simple cubic. Any question? Now I show you a very common structure. It's called sodium chloride type structure. Sodium chloride, the common salt. You see, it has sodium ion and chlorine ions. Looks like the chlorine ion at the face-centered position and sodium ion at the center of each edges. But if you look at it carefully, you can see 2 unit cells, interpenetrating unit cell. One unit cell is the sodium for sodium ion, which is face-centered cubic. Another unit cell of chlorine, which is face-centered cubic. They are penetrating each other. You can look at it that way, or you can look at this way. The sodium ions are the center of each edges, and chlorine ions are at the corner, 8 corners, as well as face-centered position. There is a pair of ions, 1 sodium ion, 1 chlorine ion, and each pair is assigned to a corner position or a face-centered position, like this. So there is a pair. Each pair is assigned to one of those 8 corner positions as well as face-centered positions. Each pair. So the Bravais lattice is face-centered cubic. Instead of 4 atoms per unit cell, you have 4 sodium ions as well as 4 chlorine ions per unit cell, because 1 sodium ion, 1 chlorine ion make a pair, and each pair is assigned to either a corner position or a face-centered position. So many materials have, like magnesium oxide, MgO, CaO, iron oxide, nickel oxide, many ceramics have this kind of structure. They are called sodium chloride type structure. However, the Bravais lattice is face-centered cubic. Any question? I prefer to keep one period of Friday for formal tutorials. You can freely ask me any question. I'll be more than happy to answer. However, at the beginning of the class, I always say, if you have any question, please ask me, I shall answer. Now look at another structure. Diamond. Carbon. 8 corners carbon atoms, 6 face center position carbon atoms, just like a face-centered cubic unit cell. However, there is a carbon atom at the interior of the crystal. Interior of the crystal. They are at a position 1/4 length of the distance along the body diagonal. Along the body diagonal, 1/4 distance from the corner, there is another carbon atoms. So essentially, you have a pair of carbon atoms assigned to each corner position as well as face-centered position of this unit cell. Look at the case. In the case of cesium chloride and sodium chloride, what we taught so far, we took a pair of cesium and chlorine atom or a pair of sodium and chlorine atom and assigned them to a point in that corresponding point lattice. Two different ions made a pair. But here, two same atoms, two same carbon atoms make a pair and occupy either a corner position of this cube or a face-centered position of this cube. These are face-centered position of this cube. And this type of structure is called diamond cubic structure. The diamonds are forever. So the diamond ring people use where the diamond has this structure. Obviously, it will have 8 carbon atoms per unit cell because 2 carbon atoms make a pair and each pair is assigned to 8 corner position as well as 6 face-centered position. The Bravais lattice is face-centered cubic, obviously, but this kind of structure if a material has, they are called diamond cubic type structure, diamond cubic. Semiconductors like silicon, germanium, tin gray, they are having diamond cubic structure. Now this is another important crystal structure called zinc blende. Zinc blende. Zinc blende type structure. I have 2 unit cells side by side of zinc blende. You can see there are 2 ions, one zinc ion, one sulfur ion. Sulfur is black, zinc is white. A pair of zinc and sulfur atoms, ions, are assigned to either these corner positions or the face-centered position. So each 8 corners and each 6 face-centered positions have a pair of zinc ions, zinc 2 plus and sulfur 2 minus. This is the structure of zinc blende, very important crystal structure. I'm holding 2 unit cells of zinc blende in front of you because the compound semiconductors, which I mentioned towards the beginning of this course, like gallium arsenide, indium antimonide, like 3,5 compounds in the periodic table, or 2,6 compounds, zinc sulfide, zinc selenide, cadmium sulfide, etc. They have this zinc blende type structure. Number of ions per unit cell, 4 zinc ions and 4 sulfur ions. The Bravais lattice is obviously face-centered cubic, but materials like gallium arsenide. You see the LED lights based on gallium arsenide, these semiconductors compound semiconductor have a zinc blende type structure. These are the 2 unit cells of zinc blende. So Bravais lattice is face-centered cubic, but structure, if it's more specifically like this zinc blende type, then they are called zinc blende type structure, just like 3,5 or 2,6 compound semiconductors. These are the structures I will mention. You will please read it up from any book. I took the slides from Shackelford books. So if you have an access to a Shackelford book, you can easily find out. In the previous one, I said zinc blende, ZNS. There is another type of ZNS called Wurtzite. In German, W is pronounced as V. Wurtzite structure. This is also zinc sulfide, but the unit cell is hexagonal instead of face-centered cubic. Number of ions per unit cell is 2 zinc, 2 plus ions, 2 sulfur, 2 minus ions. The semiconductors like zinc sulfide, cadmium sulfide, zinc oxide has this Wurtzite type structure. Obviously, Bravais lattice is hexagonal, but zinc blende in the previous slide I showed you is face-centered cubic Bravais lattice, but same zinc blende having a crystal structure of hexagonal, just like zinc sulfide, cadmium sulfide, zinc oxide have a Wurtzite type of structure. Okay, details you please put it up. Then is another structure called calcium fluoride type structure. You see I have a model in front of me. These black ions are inside, they are fluorine ions, and the calcium ions are at the corner as well as at the face center position, corner position as well as face centered position. And fluorine ions are inside. Fluorine ions located at corners of a cube at 1/4 of the distance along the body diagonal. So fluorine ions are at a distance 1/4 from the body diagonal. This is the fluorine ions. So the Bravais lattice is face-centered cubic. Number of ions per unit cell is 4 calcium ions, because 8 corner position, 6 face center position makes 4, and 8 fluorine ions, 8. They sit inside that unit cell. Materials like uranium oxide, thorium oxide, tellurium oxide, they have this kind of structure they call fluoride type of structure, calcium fluoride. Bravais lattice is obviously face-centered cubic. You may think why I'm teaching this kind of structure. You see, any materials you in future you want to study, obviously they will have a structure of one of those 14 Bravais lattices. But more specifically, you want to see that, then you see it is a fluoride type structure, zinc blende type of structure. This structure gives the properties of this material. If you want to work in the energy material, energy storage materials, whether it is a lithium-ion battery, sodium-ion battery, because energy material is one of the most important field to study now. You see the importance of this crystal structure, because when you make a battery or a cell, what do you want to do? You want to put as much charge as possible. You see, when you buy a mobile or a laptop, they say how much a single charge can give you a usage time. If you have to charge your mobile every day, all right. But if you get a mobile phone, which will require to be charged only once a week with very heavy usage, you will love it. If you have a laptop, the charge capacity is 4 hours. And if you have a laptop of the same price, same configuration, but battery is designed in such a way which will give you at least 12 hours of usage time. Which one will you prefer? The one which will give you more power. Second thing, how fast you can charge. Something requires 2 hours, 3 hours to charge, but if you have a battery, which will take say 10 minutes to charge, full charge. Will you not go for a fast charging time? So these kind of energy materials, or looking at a supercapacitor, all these designs are based on this crystal structure. How much charge you can store in the form of ions. So lithium battery, lithium ions, sodium battery, sodium ions, magnesium ion battery, magnesium ions, mixed ion battery, sodium, magnesium mixture or lithium, sodium mixture. And how fast you can charge it. This is another structure called cristobalite structure. Cristobalite. It's silicate. Brave lattice is face-centered cubic. We have a tetrahedron. This is a tetrahedron. 4 edges. Silicate tetrahedron SiO4, 4 minus. At 4 corners of this tetrahedron, we have an oxygen ion, these 4 corners, and silicon ion sits in the center. And what I do, I take a tetrahedron having 1 silicon ion and 4 oxygen ion as a part of this tetrahedron, and we assign a tetrahedron with respect to a lattice point. That's the reason at the beginning of this chapter I mentioned, instead of looking at an individual atoms, look at imaginary points, how they are arranged in periodic fashion in space. And then you take an atom or a group of atoms and assign to those lattice points. That will be a lot easier. I can describe how SiO4 is arranged. 4 oxygen ions are the 4 corners of a tetrahedron and silicon ion is in the center. I can easily explain. And then I can more easily explain the fact that each tetrahedron occupies either a corner position or a face-centered position. That makes cristobalite. It is a crystal structure of silica, just like quartz. Face-centered cubic, and each unit cell has 8 silicon 4 plus ion and 16 oxygen 2 minus ions. This is how you explain the structure of cristobalite. Any modern materials you want to design, a very advanced material, or try to understand the properties of the existing materials, without the crystal structure, you cannot do that. Okay, few things, you read it up. Corundum, L2O3, from the textbook. Structure, I'll not expand. Perovskite, extremely important structure for various materials, including energy materials. Perovskite. Read that thing. This is simple cubic. Looks very complicated, but it's simple cubic. Read on your own. Spinel, for any modern materials you want to design, and ceramics also. Spinel is a very important crystal structure. These things, what I am asking you to study from the book, it will come in the exam for sure. Kaolinite, that you read. Okay. This clay plated. Diamond cubic I just showed you. This is the structure of diamond cubic, which I mentioned. Brave lattice face-centered cubic. More specifically, it is called diamond cubic. But look at the same carbon atoms. If they are arranged in this hexagonal form, and these are the basal plane, this is the structure of graphite. Graphite layer structure. The so-called anode or the negative electrodes of a lithium-ion battery, which I showed you, the anode and cathode material and the electrolyte at the introductory classes. The lithium ion during charging diffuses inside these layers of carbon, and during discharging they come out, lithium ions. This is how you store charge in the graphite anode or negative electrode of a lithium ion battery. The same carbon, C60 molecule, or more commonly known as buckyball. This is how They are arranged just like a football. Hexagon and pentagon arrangement, you create a buckyball. This is another crystal structure of same carbon atom. Carbon nanotube, same thing. These are the polymeric chains of polyethylene. Carbon is present. This polymer structure I will not teach you. Towards the end of the class semester, I'll mention few things. So what we learned here, 7 crystal systems, putting positions other than those corner, I got 7 more, so 14 Brave lattices. And next class, I'll end here because a lot of things I covered in one day. You need to have time to absorb these things. I'll talk about coordinates, crystal directions, and planes. How do you index it? After covering that portion, I shall move to the next chapter, chapter 4, atomic level defects in crystalline solids. So I end this class here, but now I am available to answer any question you may have.
Can you explain the structure of crystalline again?
This is a face-centered cubic Brave lattice. There is a tetragon at 8 corners and 6 face-centered position. And tetragon at 4 corners, you have oxygen ions, and at the center of the tetragon, you have a silicon ion. So silicon 4 plus, oxygen 2 minus. So each tetragon has a silicon 4 plus at its center and oxygen 2 minus at 4 corners. And each such tetragon is assigned to 8 corners and 6 face-centered position. Am I clear to you?
So means in terms of voids and lattice points, can you mark which ones are oxygen and which ones silicon?
If you look at a tetrahedron, at the center of the tetrahedron, you have an oxygen, a silicon ion, and there are 4 corners of a tetrahedron where you have oxygen ions. Any other question?
Sir,
Look
why
at
are there
this.
8?
I have
Hello?
a tetrahedron. 4, can you see me? There are 4 corners. At the 4 corners, I have oxygen ion. At the center of the tetrahedron, these black balls, it is my silicon ion. That makes SiO4 4 minus. So this is the tetrahedron. Oxygen at 4 corners. These 4 corners I have oxygen. And in the center of the tetrahedron, I have a silicon ion, these black balls. So in face-centered cubic, at each corner, I put a tetrahedron, and each face-centered position, I put it a tetrahedron. Any other question? Any other question? Hello?
Yes, sir, you're audible.
Anybody has any other question?